Welcome back to my channel. Here I do problems in chemistry and physics. If you like this content, please like and subscribe, as well as check information below this video about my online tutoring service. In this video, I'm going to consider some questions about Lewis structures, bond length, and hybridization. Consider the Lewis structures for the following molecules: CO2, CO3 2 negative, NO2 negative, and NO3 negative. Which molecule would have the shortest bonds? Now, to answer all of these questions, we of course want to draw Lewis structures for these four species. We're going to start with drawing the structures of individual atoms for carbon, oxygen, and nitrogen. So carbon is in group 14. Therefore, it has 4 valence electrons, group 14. Nitrogen is group 15. It has 5. And oxygen is group 16, so it has 6 valence electrons. Okay, to draw a Lewis structure, we're going to start with CO2. The first thing we want to do is determine the total number of valence electrons in the structure. So CO2 has 1 carbon and 2 oxygens. That means that it's going to have 4 for carbon plus 6 times 2 for oxygen. That's 12 plus 4. That's 16 valence electrons in the structure. Okay, you're going to start drawing it with carbon in the center. Bond oxygens first with single bonds to the central atom. By the way, each single bond is using 2 valence electrons. It's a pair. Okay, then you're gonna see that carbon can actually bond twice to each oxygen. So you can add a second bond to each oxygen. Carbon already has a completed octet. That's 8 valence electrons outside of carbon atom, on the outside shell. Now we're going to complete oxygens with the rest of the electrons to make up 16 total. So now we have 4 bonds. That's 8, 9, 10, 11, 12. Now this carbon also has an octet. That was 12, 13, 14, 15, 16. So now we have a total number of 16, and every atom here has a completed octet of 8 valence electrons. Okay, next we're going to do CO3 2 negative. So CO3 2 negative. Now this one has 1 carbon, that's 4 plus 3 oxygens, 6 times 3, plus 2 extra electrons for the net 2 negative charge. Each negative charge is an extra electron, so 2 extra. And the total here is 24 valence electrons in this structure. Now, we're going to draw with putting carbon in the center. Put oxygens around it. First bond with single bonds only. Then you're going to see that, okay, carbon already made 3 bonds. It has 4 valence electrons, so it can have 1 more bond. You could think, okay, can I leave just 1 electron like that and not even bond it to anything? Well, the answer is no. You don't want to leave any single valence electrons, single dots. They're extremely unstable. They're called radicals, by the way. The structure that has them is called a radical, so you don't want to leave single valence electrons. That's not allowed. You want to pair it to something. Well, you can only pair it to oxygen here, so make a double bond to one of the oxygens. Now that's using 1, 2, 3, 4 times 2. That's 8. 8 electrons used. Carbon has an octet. Let's continue to put the rest of the electrons. Now let's finish off this carbon. That's it already has 4, completed with 4 more. Now it has an octet. Now this one has 2 electrons. We're going to complete it with an octet with 6 to make an octet. Now that's using 1, 2, 3, 4, 8. It's going to be 10, 12, 14, 16, 18. We can put 6 more to make it a 24. Put them on another oxygen, and now we can see that every oxygen here has an octet, and the carbon also has an octet. Okay, we are done. Okay, and the net charge is 2 negative. You can put it in brackets like this and show 2 negative net charge. Okay, next structure is NO2 negative. So NO2 negative is going to have 5 valence electrons for nitrogen plus 6 times 2 for 2 oxygens plus 1 extra for negative charge. That's going to be 18 valence electrons in the structure. So we're going to put nitrogen in the center, pair with single bonds first to oxygens. That's using 4 valence electrons. Now nitrogen has 5 total. It's making 2 bonds, so you can use 3 more electrons. Now I can put 1 pair, and I have 1 electron left. Where do I put it? I can't make it single. That's not allowed. So let's make another bond to one of the oxygens. So now nitrogen has an octet. Let's finish this oxygen, and I'm using 1, 2, 3, 4. That's going to be 8 electrons. I have 10 more. 9, 10, 11, 12. This one has an octet. 13, 14, 15, 16, 17, 18. So now I'm using 18 electrons, and the net charge is -2. Every element here has an octet. You're done with this one. By the way, always double check that whether your elements will follow the octet rule, because all of these elements here, they're in the second period, so they're obligated to follow the octet rule. You cannot, there is no available empty d orbitals like for elements in higher periods, so there is no way to have more than 8. They have to follow octet rule. That's their stable configuration. Okay, so and the last one is NO3 negative. So NO3 negative, nitrate. Now this one has 5 for nitrogen plus 6 times 3, 18 for oxygens, and 1 extra for the negative charge. That's 24 valence electrons for nitrate. Now I'm going to put nitrogen in the middle, make 3 single bonds first. That's using 6. Now I have a pair of nitrogen. That's not going to go anywhere, right there. That's using 8. I'm going to start with one of the oxygens. Actually, I'm going to put, now that was 8, 10, 12, 14, 16, 18, and 20. So I have 4 more electrons, and I'm going to complete an octet on 2 of the oxygens. But here, so I completed an octet on the nitrogen and on 2 of the oxygens. However, one of my oxygens, that's this one, only has 6 valence electrons. That's not good. That's not a stable configuration. So, and I ran out of electrons already. So what I'm going to do is move this pair, this lone pair. I'm going to make a bond out of it. Yes, this is allowed. A lone or unshared pair can make a bond with an element which has an empty available orbital, like this oxygen. And now I have to erase this pair. And now all of my atoms are in the octet configuration, all of my oxygens, and nitrogen also. And I'm using all of the 24 electrons. And the net charge on nitrate is -1. So now I can answer the first question. Which molecule have the shortest bonds? Okay, the rule is that the higher the bond order, the shorter the bond. So we're going to have to consider here bond order. And the bond order is lowest for single bonds, that's bond order 1. The next comes a double bond, that's bond order 2. Next comes a triple bond, that's bond order 3. So as we can see here, and by the way, if you have a mixture of different bonds in the molecule, you can find an average bond order. I'll show you how it works. So let's look at carbon dioxide. It has 2 double bonds. So that's 2 for each bond, 2 plus 2. Divide by the total number of bonds, that's 2 bonds. So here the bond order, the average bond order in the molecule is 2, which is self-explanatory because it only has double bonds. Now let's look at carbonate, CO3 2 negative. Here you have a double bond, so that's bond order 2, and then you have 2 single bonds, that's plus 1 plus 1. The total number of bonds is 3 divided by 3, so that's 4 divided by 3, 1.33. The average bond order in this ion. Let's look at nitrate. This is nitrite, NO2 negative. So it has a double bond, that's bond order 2, plus a single bond, bond order 1, divided by 2, because it has 2 bonds. That's the average bond order of 1.5. And nitrate is going to be the same as carbonate. I can see it because it's a double bond and 2 single bonds. So the bond order is going to be 1.33. Okay, and again, the shortest bonds are the bonds with the higher bond order. So the double bond is shorter than the single, and the triple is shorter than the double. More shared pairs kind of make the bond, also make it stronger and shorter, because there is more attraction between the electron cloud and the nuclei of the bonding atoms. So the winner here clearly is CO2, which only has double bonds, so bond order 2, and the answer is A. Next question. Which molecules are best represented by multiple resonance structures? Okay, what is resonance? Resonance structures are variations of Lewis structures with different arrangements of bonds, however, which show the same or equivalent structures of the molecule. So again, these are different arrangements of bonds in the same structure which are equivalent to each other. So let's look at CO2. We can't really rearrange these bonds in any manner. It's still going to be 2 double bonds. So there is no resonance for CO2. By the way, this thought allows me to choose the correct answer because, well, no, actually I have to look at B, C, and D. So let's keep going. Now, the CO3 2 negative. Look what you can do here. I can draw 2 more equivalent structures for CO3 because this double bond doesn't have to be here. I can draw another structure which is going to look like this. It's going to have a double bond, let's say, on the bottom, and single bonds to these oxygens. Or I can draw a double bond to the oxygen on the right, and so I can draw 3 equivalent structures for CO3. In fact, if you were to measure these bonds, you wouldn't be able to determine which one is a double bond. So all of these bonds will have the same length and energy. So they are equivalent, all of these bonds. that's how you know that you actually can have these resonance structures. So yes, for CO3 we can draw 3 resonance structures. What about NO2? Yes, we can move this double bond to the other side and get another equivalent Lewis structure for it. So yes, you can draw two resonance structures for NO2. And also for NO3, you can move the double bond here or here. They're all going to be equivalent bonds and equivalent structures. You can draw 3 resonance structures for NO3. So all of these except for CO2 can be represented by multiple resonance structures. So the correct answer here is D. Okay, which molecule or molecules exhibit sp2 hybridization around the central atom? Okay, what is sp2 hybridization? It's mixing, basically it's mixing of one s orbital and 2 p orbitals when they create sigma bonds. Now, I don't want to go too deep in discussion what's sigma bonds, but basically, if you have any bonds between two atoms, the single bonds are going to be sigma bonds. They are positioned on the straight line between the nuclei. So they connect atoms at a straight line between the nuclei. Those are sigma bonds. But in a double bond, you only have one sigma bond, and the other bond is pi bond. So basically, you're looking at 3 sigma bonds or lone pairs in the structure to the central atom. Or lone pairs. So you also have to include lone pairs. So we can say we're looking for a total of 3 charge groups to the central atom, which includes lone or unshared pairs of electrons. Now, let's look at CO2. So CO2 only has 2 charge groups around the central atom. There are no lone pairs. So this one is not sp2. It is actually sp hybridized carbon here. So CO2 is not sp2 hybridized. Let's look at CO3. You have 3 sigma bonds around carbon, no lone pairs. So yes, you have 3 charge groups, and yes, this one is sp2 hybridized. sp2. Because again, those sigma bonds are created by mixing the s orbital and 2 of the p orbitals, and all of these bonds are equivalent in the structure because of hybridization. Now, in the NO2 negative, you have 2 sigma bonds, but also you have this lone pair. So yes, you have 3 charge groups around the central atom, and yes, this structure is also sp2 hybridized. And the last one is NO3. Yes, you have 3 charge groups around the central nitrogen, no lone pairs, but you do have 3 charge groups. So that's also sp2 hybridized structure. So our answer is D. Everything except for CO2 is sp2 hybridized here. As you can see, in this group of questions, everything starts with drawing the structures. Once you have the correct Lewis structures for these molecules, everything else really becomes very obvious about answering these questions.